Okay, good morning, everyone. We start, of course, I ask you about your questions. Do you have any questions from the homework? Today we're going to have one more new idea, and then the rest of the hour we will be, basically answering all your questions about the review. But first, any questions from the homework? Anybody? Please put them on the chat if you have any, and then I'll move on to the exam. Okay. All right. So I will start by, since we're going to talk about basis a little bit more today, we'll start, but first I want to start by commenting about the quiz. So comment about the quiz. Usually I comment about the two mistakes that actually was the most done in class. The first comment was about reflect, rotate. So there is the idea of reflect, rotate versus rotate, reflect. Okay, so it's really one of your questions on your quiz. Now, my question to you is, if you reflect, then you rotate. Is it the same thing than rotating than reflecting geometrically? Are those two transformations the same? I mean, do they give you the same output? And absolutely not. And that's important because if you take a vector, you rotate it, and then let us say reflecting across, so that's this one, reflecting across the x2 axis, and it's going to end up right there. Now, if you reflect and you rotate, it means you're taking a vector, you're reflecting, you're right here, and then you're rotating that vector. So they are absolutely two different transformations. This is one of the mistakes that really came up. So how did you, I'll go over the problem that was given on your quiz. So I asked you, if my memory is correct, I forgot to put the quiz in front of me. So I asked you that, let's give the transformation that first rotate by pi over 6, and then reflect. That was the transformation across the x2 axis. And the idea what the standard matrix of that. So we're working, we mentioned in class, and we gave you exercise to find the standard matrix. It's enough to find what T does to the two-unit vector E1 and E2, basically the I and J vector. So I started studying what happened to E1. E1 is the I vector, it's the 1, 0. I rotated first, and that's why some of the mistake came up. So first, I rotate that. To find out where the vector ends up, we multiply it by the rotation matrix. So first I'm taking, so geometrically, keep the picture in your mind what you're doing. You're taking basically the vector E1, that's the unit vector here. You're rotating it, you're gonna land here, and then it's this one that we reflect. So if you a little bit do some geometry, it helps you to find out whether your answers are correct or not. So now the rotation matrix was the cosine of pi over 6, the sine minus the sine, and the cosine. Means this vector, after I rotate it, is going to end up right here. I am at this stage of the picture. And it's this one that you reflect across the x2 axis. Now, this is an easy problem. It means if this is the vector square root, you reflect it. Now, of course, the y component remains the same, and the x component is negative. So we know exactly where it's going to happen to it. Now, let us say we do a transformation a bit harder than reflection across the x2 axis, and you want to know where it goes. What you do is you take the matrix that gives you reflection and you multiply it by the vector. Now, which matrix I'm talking about? What's the matrix what's the standard matrix of the reflection across the x2 axis? Always, the first column is going to be what does the reflection do to the E1 vector. So this is just to figure out. So to the E1 vector, the reflection across the x2 axis is going to send it right there. And the E2, the reflection, will keep it exactly where it is. So this is the reflection across the x2 axis. Now I just compute that, and I'm going to get minus the square root of 3 over 2 and a half. And at least the picture makes sense, because this vector is minus, at least the x component is negative and the y component is positive. So this tells you that if you get minus minus, you're doing something wrong, because the picture tells you should get positive in the two conditions. Okay, so the mistake that the student did was, memory is right, some of them, not of course, not a lot, they actually did the reflection of the vector 1, 0, and then they rotated it, and that was absolutely wrong. Okay, so that's comment about one of the problems you have in the quiz. For E2, you guys look up the solution. It's very clear by now. The other mistake that was done is in the last problem about subspaces, and most of the mistake was due to lack of understanding of the OR in math. So the OR, as I wrote to a lot of you, means either one of them or both. So when I told you let H be all the vector x1, x2, such that x1 is 0 or x2 equal to 0, it means either one of them is 0 or both of 0. So the first problem was a lot of you picked up the 0 vector. As I said, the 0 vector is not in H, and this is absolutely wrong. 0 vector is in H, because all mean one of them. Of course, the first component is 0, I am down. So that was what got a lot of you in this problem. And that is a subspace. The answer was this not a subspace because 1, 0 is in it and 0, 1 is in H. But when we add them, this is not in H. So this is in H because one of the component is 0. This is in H because one of the component is 0. This is not in H. Now, what is the geometric, how can we visualize H geometrically? Now I'm asking you the question. How can we visualize H? What is H? It's not hard. I would like an answer on the chat or somebody in mute and answer. What is H geometrically?
The axes, X and Y.
Right, it's the axis is either x1, 0 or x2, 0. So if x1 is 0, it means your vector has to be here. If x2 is 0, it means your vector has to be here. So x1 or x2 is 0, it means everything that lies either on the x1 or the x2 axis. And this is definitely not a subspace because this is in it, this is in it. But when you add them, you're out of it. And that's the geometry behind this problem. Okay, so this is comments about the quiz. Now we go back to bases, and since So first, let us recall what is a basis. Who would like to tell me what a basis is? So we start with a subspace. And as I said before, to help you with the geometry a little bit, to imagine something, when I say H is a subspace, so I want you to imagine if you are in R3, put in your mind, I'm talking about a plane through the origin, a line through the origin, all of R3. Keep this image in your head so you can actually interact with the material. So H, let H be a subspace, and I have a bunch of vectors in it. In H, 2, 3, 4, whatever. So they form a basis if. All right, who would like to tell me what's the definition of a base? What does it mean those vectors form a basis? Please hurry up because we'll be tested on it. It's important. Anybody would like?
It's a linearly independent set in H that spans H.
Right, crucial. So it's a set of vectors, but that every vector in H is a linear combination. So their span is everything. Everything in H can be basically obtained from them, anything. And they have to be linearly independent because I don't want a lot. I want the minimum number of vectors that will span H. So I don't want redundancy. I don't want vectors which depend on others because they really actually are not important for me. So basically the bases are intuitively, I'm looking what we call it the minimum spanning set. It means I'm looking for the minimum number of vectors necessary to span the subspace, the minimum vector. I don't want a lot of them. I don't want redundancy in my vectors. I want the minimum needed to span my whole space. So this is the definition of a basis. So I'm going to do only 2 problems. Last time I did it a lot in R2. I'm going to do 2 problems in R3, and then we move on. So I will look at problems in your book, actually. And I like number 17. My subspace now is R3. So this is that's the subspace. And I'm going to take a bunch of vectors, 0, 1, minus 2, and 5, minus 1, 4. And my third vector is the following, 6, 3, 5. And the question is, do they form a basis in R3? Okay, do they form a basis? So what do you think? Yes, no, we don't know. Yes or no, or we don't know. I want an answer.
Maybe we don't know.
Maybe we don't know. Why?
Don't we have to check them to make sure they are linearly independent?
Exactly, we have to check that first. So we have 3 vectors in R3. Anything can happen. So first we check the linear independence. So we check it. It means we have to solve this equation and see if we have non-zero weight that satisfy this equation. If we have non-zero weight, it means one of them is a linear combination of the other. It means they are dependent. So I will not do the whole problem. I mean, so 0, 1, 5, minus 7, 4, 6, 3, 5. And I'm gonna I actually do the minimum needed to check out if they are independent or not. I don't have really to do the whole work. As long as I have a pivot in every column, I am actually safe. So if I do the minimum possible, I definitely have to switch rows because I have a 0 in here. And I do a little bit, somehow I've done this, and I have my notes here, 0. Is this enough? Remember, be careful, I did not go to the reduced echelon form. I did not really make those into 1, but will this give me enough info to see whether they are independent or not? What can we say here? Absolutely, I have a pivot in every column. That's homogeneous. So of course, I don't have to worry about consistency. I have a pivot in every column. So if I solve this, I get C3 equals 0. I solve this, I get C2 equal to 0. I solve this, I get C1 equal to 0. So solving that, I get C3, C2 is 0, and C1 equal to 0. So those three vectors are linearly independent. Okay, so the first properties is absolutely satisfied. Now we still have to worry about the second one, so that's the linear independence. Now, is the span equal R3?
Yes.
Immediately. Can we immediately say yes? Because there are three vectors. Be very careful. If I have two, the linear independence, big deal. It doesn't give me. Every vector has to be, so you can here either invoke the invertible matrix theorem that tell me any three linearly independent vectors in R3 span R3, or you can actually justify it by telling me, you know, if you take any vector here, sorry, any vector here, and you try to find if this is in the span, when I go to the echelon form, I know that I have a pivot right there in every row. So there is no room for inconsistency. So when I solve, because I have a pivot in every row, not column now, in every row, there is no room for inconsistency. So this is always consistent, regardless what vector B I plop in here. So consistent, it means the span equal to R3. Every vector could be written as a linear combination, so it's absolutely a basis. Okay, so that's really for R3. So first we have to check linear independence, and after that, we are safe. Now, but you have to check linear independence. So if they are linearly dependent, you're done. So the question now, what if I have that? Can those form a basis? Yes or no, quickly. And which property fail? Do they form, sorry, basis for R3? Means my subspace is R3. I want to cover all of R3. So do they form a basis? Yes, no?
No.
Justify. No, because
the span is not R3.
The span is not R3. You have two vectors. Even if they are linearly independent, which is I think they are in this scenario, it doesn't really matter. The spanning property is absolutely not satisfied. And basically, two vectors span a plane. Or if you try to solve the system, 3 minus 8, 1, 6, 2, minus 3, and you put a vector B in here, okay, since we have this row will have to be 0, and this is going to be the picture. So of course, I can create a B that cause inconsistency. It means not every B could be written as a linear combination. So that's the algebra behind it. So now, as we did last time, if I have 4 vectors in R3, it's the dependency, which is the independency, which is not satisfied. So 4 vectors in R3 is, there is no way they can form a basis. And this actually motivates the definition of a dimension of a subspace. So suppose H, and that's what we mean, a subspace of Rn, then the dimension of H. I forgot to write this in the lecture note. So the dimension of H, which is written as dimension of H, is the number. It's a number of vectors in a basis for H. Okay, so dimension of a subspace is how many vectors there are in a basis. And this is definitely coincide with a little bit our intuition of dimension, but this is the definition of dimension in math. It's the number of vectors in a basis for H. So now based on this definition, the dimension of R3 is 3, because 3 vectors are needed to cover all of R3. That's the minimum number of vectors you need. You can cover R3 with 4 or 5 vectors, but basis requires inevitably the minimum vector needed to cover the space. And with this in mind, the dimension of R2 is equal to 2. Okay. Now let me two more examples before I go back to the null. So question number 1 is also, let me take H to be the following subspace. All the vector x1, x2, x3, such that x3 equal to 0. Okay, and my question to you is, find a basis for H. Find a basis for H. First, H is in R3. Let's get that straight. This is in R3 because every vector here have 3 entries. And I want you to find a basis for H. And this problem, I want it geometric because idea is to build your geometric intuition. What is H geometrically? And how
The
can I
x1,
find the
x2
basis?
plane.
Right, it's the x1, x2 planes. Is this a subspace? Is this plane? Is this a subspace? What do you think? Is it going to verify all the property of a subspace? 0 is in it because the third component of the 0 vector is 0. If I add 2 vectors, so H is everything of the form x1, x2, 0. That's H. If I take 2 vectors that have this property, add them, of course, it's going to carry the same property because the third component is 0. If I take a vector that have this property and I scale it, the new vector will also have the same property because this is a 0 vector. So it's a subspace, it's a plane through the origin. Now who can give me a basis for this subspace? Or who can give me vectors linearly independent and such that everything in here is their linear combination? I mean, they cover all of H. You have a minute to do that because it's an easy question.
1, 0, 0, and 0, 1, 0.
You agree with absolutely? It's not E1. Yeah, it's E1 and TE2 in R3. Absolutely correct. So the basis here is fairly simple. So it's fairly simple basis. So it's 1, 0, 0. It's of course in H. The third component is 0 and 0, 1, 0. It's also in H because the third component is 0. They are obviously linearly independent, and any vector in H could be written as a linear combination. So this is absolutely satisfied. So that's the subspace, and this is the basis for it. And now what's the dimension of H? What's the dimension of H?
2.
2. That's the dimension. So, and it's really follow our intuition. The dimension of H is 2. So H, we call H a subspace of dimension 2 in R3. So it's in R3. It's not the plane. It's not R2. It is in R3, but we say it's a subspace of dimension 2 in R3. It means 2 vectors are needed to span all of H. Okay. Now I'm gonna again give you a small problem again to emphasize the idea of a basis. So this is my question to you. Okay, I'm not gonna answer it. I'm gonna give you a few minutes to answer. Suppose I say let H be a subspace of R4. Now it means I picked R4 on purpose. It means H is collection of vectors in R4 that have the properties of the subspace. So 2 vectors in here, stays in here, stretch a vector in H, is remain in H. And you're given that. You're given the following, that those vectors, so they are in R4 because that's our universe, that's where we live right now. 1, 2, 0, 1, minus 1, 3, 1, 2, you're given that those form a basis for H. Okay, the idea here, the question is to, and now here's my question. Is the vector, is the following vector, minus 5, 0, 2, 1 in H? Okay, so I put this problem in front of you and I want you to read it a second time and interact with it yourself. And tell me, am I making sense to you? Did I give you enough information to be able to answer the question? Yes or no?
Yes.
Okay. Anybody else? Did I give you enough info? So I told you it's a subspace. It means it has certain property. And I gave you a basis for it. So, okay, Bradley, say yes. Anybody else say yes? Okay, now justification. Whoever say yes, please feel, Mika, are you comfortable answering the question? Mika or anybody else? Anybody is comfortable telling me whether I gave you enough info, yes or no? And how can I answer this question? Anybody feel comfortable unmuting and tell me the answer?
If those two vectors form a basis of H, they're in
Yes.
H, so you can check to see if X is a linear combination of those two.
Absolutely correct. Because if I tell you those form a basis, what info I am telling you? I'm telling you two things. First, they are linear independent. Big deal. We know that. But the most important thing I'm telling you also that everything in H is a linear combination. So by telling you they form a basis, it means I'm giving you the very important information. I'm basically telling you what H is. I'm basically telling you that H is nothing more than the span. So giving you a basis, it means I'm giving you everything. I'm basically giving you the subspace. So I'm telling you that this is equal to that. That's the importance of a basis. Now, is X in H? It's really boiling down to ask yourself the question, is X a linear combination of those two vectors? So is X in H? So that's equivalent to us. Is X a linear combination, sorry, of my vector, let me call this V1, let me call this V2, of V1 and V2. That's really what the problem really boils down. So the idea that giving you a basis, that's why those are important, means that instead of giving you all possible vector in H, I tell you, you know, this is their basis. It means everything is obtained as a linear combination. That's the importance of a basis. So now, is X is a basis, we try to ask ourselves, I set up my system, and so this is my H, so 1, 2, 0, 1, and minus 1, 3, 1, 2, and my vector X is minus 5, 0, 2, 1. So, and basically I'm solving the system C1, V1 plus C2, V2 equal to B. Okay, now we have to do the math, and I did it. So you go to the echelon form and you get that. You don't have to go to the reduce, but at least the echelon form. And I got a 2 in here, and I did 1, minus 1, and I got a minus 5 in here. So what will be the answers? Is X, this vector linear combination? Absolutely yes, because the system is consistent. I have 0, 0, 0, 0, 0, 0. And if I solve, I get that my vector X, which is this one, that's my vector X, I can write it as a combination. It's 2 times the vector minus 1, 3, 1, 2. And if I solve for the first weight, I get minus 5 plus 2. So it's going to give me minus 3 times my vectors. So this vector is in H. So the point here, as I said, giving you the basis, give you everything you need about your space. And that's really basically that's really the extreme importance of the idea of a basis. Right, so the last new idea, I mean, this is what I've done so far is to help us understand the basis. The last idea is I'm going to go back to the null space and find a basis for it. Last time we defined it, and I showed you that it's a subspace. So let us remember the definition always. Suppose you have a matrix A. What is the null? I'm waiting for answers. A is a basis. What is, sorry, A is a matrix. What is the null? Null should remind you zeros. What's the null? Quickly.
Null space contains all the vectors that satisfy the equation A times that vector is equal to 0.
Right. All the solution, exactly. All the solution of the homogeneous system AX equal to 0. So the null or all the vectors are those. At which those, all those that make AX equal to 0. Last time I showed this is a subspace, meaning I convinced you that if X and Y solve the system, their sum will solve the homogeneous system. If X is a vector and you scale it, so and X solve the system X equal to 0, C times X will also solve it. So that's really a subspace. Now we're going to find a basis. It means how to find, so there are tons of vectors in the null. There are infinitely many of them. Not one, not two, there are infinitely many of them. So the question is, how can I find the minimum number of vectors so that the null is nothing more than their span? It means how can I give you just find a bunch of vectors so that everything in the null is their linear combination. So instead of giving you all the solution, I give you only those bases. And then you can figure out everything else. All right, so that's really what we're going to do today. It's fairly easy. It's actually surprisingly easy. And we've done it a million times without mentioning it. So recall that the null is all the solution of AX equal to 0. And what we're going to show is how to find a basis. And we'll show you that by an example because that's the easy way. So I have my matrix, minus 3, 1, 2, etc. And we're going to find a basis. To be able to find it, first I want to find those vectors. Sorry, I need to find the axis such that AX equal to 0. So I cannot find a basis if I don't know what is in the null, what type of vector. So the step number 1 is we need to solve the system AX equal to 0. And we're going to write the solution in parametric vector form. So we solve it. So we take A0, we go to the echelon form, and most of the time, especially if the matrix is hard, I will give you on the exam the echelon form, so to save you a lot of work. So we start with the system, and you go to the echelon form, and then we solve. So let us remember how we solve. So I'm gonna hide this a little bit. My basics, x1, x2, sorry, x3. My free variable are x2 and x4. Okay, and let us always remember, or what's crucial to always pay attention to is the following. Always ask yourself, the vector x that solves the system x equal to 0, how many entries should they have? Always try to ask yourself, how many entries? So this is A, have 4 columns, so my vector x has to be in R4. So always ask yourself, where is my vector? Actually, I have here 4 components. So now that's solved. So we write the equation that the system that corresponds to this echelon form. So x2, x4 is free. The first one give me x1 minus 2x2 minus x4, 0, and x3 plus 2x4 equal to 0. Now, how do we write this in parametric vector form? And this is going to be the key to finding a basis. That's why it is important. So we set the variable x2 to be s, x4 t, and we're going to express everything in terms of the free variable only. All right, and of course we've done this a lot, so it's nothing new now. So x4 is my t, x2 is my s, and then I solve for x3 minus 2x4. x3 is minus 2t. And I solve for x1. x1 is 2x2 plus x4. It means 2s plus t. And now we have to write the solution in vector form. And I repeat, this is going to be the key because this is going to give us the basis. So we write it in vector form, and let's see how we're going to write it. So this is my solution, x1 to s plus t, s minus 2t and t. And how we write it in parametric vector form, we try to basically put the s and t, somehow try to get them out of the vector notation. To be able to do that, we have basically to split the vectors. So it's going to be s times 2, 1, 0, 0, and the t 1, 0, minus 2, 1, where s and t can take any value. So what does this tell me? Tells me that every vector in the null, it means every vector that solves the system, is a scalar times that plus a scalar times this. Will this be enough to give me a basis for the null? So let me move a little bit further. What does this show? Everything in the null is a linear combination of this vector and that vector. So what this way of writing it in parametric vector form is telling me the important information that any vector that solves ax equal to 0 is a linear combination of that and that. So which means that the null is nothing more than the span of those two vectors. Everything is a linear combination. Means if I give you those two vectors, I tell you, okay, those span the null, I'm giving you everything in the null. It means every solution is a linear combination. So writing it as a parametric vector form is actually helping me to find the vector that span the null. Now, those two vectors are obviously linearly independent. We can check it, but since they are two, they are also not scalar multiple of each other. So moreover, the vectors are linearly independent, hence they form a basis for the null. So the basis for the null is going to be those two vectors we're getting when we write the solution in parametric vector form. Those will be the one which will form the basis for the null. So they give me every possible vector, every possible solution of the system ax equal to 0. So finding a basis for the null is actually not hard. You write the system in parametric vector form. Once you write it in parametric vector form, you have it. You have your basis. So now, what's the dimension of the null? The dimension of the null is the number of basis vectors in the null. There are two vectors in the basis. It means the dimension is equal to 2. But the null itself is where?
R4.
Yeah, it's important. The null itself is in R4 because the vectors in the null have 4 components. So the null itself is in R4, but it's dimension 2. And algebraically we say that the null of A is a subspace of dimension 2 in R4. The dimension 2 tells you that you need 2 vectors to span all of the null. So you are in R4, but the null is obtained by spanning 2 vectors. They are enough to cover all of the null. Please ask questions as I move on. Because this will be on your test, on your exam, but I know that it's not hard. That's why I usually feel comfortable. All right. So I'm gonna do 2 practice problems. The first one is, again, to tell you that work with our intuition. So the first one, let H, this is a problem that we can do it by looking at it. So we can do it geometrically or we can do it algebraically. So let H be, that's number 1. all the vectors x1, x2, x3, such that x1 minus 2x2 plus 3x3 equal to 0. Now, by now, I think all of you have done 260, the basics of calculus 3. And geometrically, this is what? So if I call this x, y, z, this x1, x minus 2y plus 3z equal to 0. That's exactly the equation of a plane that goes through the origin. So this is actually a plane, absolutely a plane that goes through the origin. And my question is, we want to find a basis for h. As I said, I can do this purely geometrically or algebraically. It means I want to find vectors, but that anything that satisfies this condition, anything in H is a linear combination. Okay, how many vectors I'm going to get in the basis? How many vectors do I need to cover a plane? 2, 3, 4? Quickly? Absolutely 2. I need 2 vectors to cover a plane, and the question is, let's figure them out. Okay, and that's to work with our intuition. I mean, the whole idea is our intuition at work, absolutely. So one way to do this is, I'm gonna look at x1 minus 2x2 plus 3x3 equal to 0. This is nothing more. So the element in H are solution of the following system. Ax equal to 0, where A is the matrix 1 minus 2, 3. So that's one way you can look at this problem. So we're going to solve Ax equal to 0. It means I'm going to solve x1 minus 2x2 plus 3x3 equal to 0. All right, I set it up. I know it's weird because it's one row, but this is not a big deal. How can I solve this? Of course, that's going to be free. X is free. X3 is free. X2 is free. X1 is 2x2 minus 3x3. There is no way out to solve this equation. X3 can take any value. X2 can take any value. If I know x2 and x3, then x1 will be dependent or constrained on x2 and x3. So we're going to write them in parametric vector form. That's the way we move. X is, I put x2 to be s, x3 to be t. So x1 is going to be 2s minus 3t. So I decompose it. 2s minus 3t, that's for x1. x2 is s. And x3 is equal to 0. So every vector in this plane is actually a linear combination of those 2 vectors. So H is their span, and a basis for H is actually 210 minus 301. This forms a basis for H. And we expected 2 vectors because it's a plane. So the dimension of H is equal to 2. So basically, the whole thing, what I am doing is what our intuition tells me. This is my vector H. Sorry, H for me, it's a plane. So that's my H. It is a plane. And I'm finding a basis. I actually need 2 vectors. This is really what I need. And what this is giving me, what I did a minute ago, what this is giving me, they are giving me those 2 vectors. So they are telling me this vector is in H, and this is a vector. And this is the equation of my H. I will pull up the paper in a minute. Sorry, okay. So this is the picture here. This is my plane, that's my H. And the vector 210 is of course in H. If I plug in 2 minus 2, 0, this is definitely in H. Minus 3 plus 3, 0. And this is telling me that those 2 vectors form a basis for H. And this is really work with our intuition again, because we know that we need 2 vectors to span a plane. And if those 2 vectors, we go back to day 1 of the course. If you are in a plane, and those, you can think of those as 2 directions in the plane, which are independent, and everything could be obtained, basically anything, you can reach any place in the plane by following those 2 directions. So those form a basis for each. All right, my last practice problem is, I will look at it, but so we can a little bit work on it together. So my last one is, just practice. So we have this huge matrix, and you're given that the reduced echelon form is that. I usually give you the reduced echelon form, the book does, and I will. And the question is find the basis for the null. Question number 1, and state its dimension. Question number 1, the null is where? It means vectors in the null, how many components do they have? This is your A. How many components do they have? Quickly. Absolutely 5. You always ask yourself how many components. So if you ever forget, you ask yourself, okay, AX equal to 0 is a system with how many unknowns? Since you're multiplying by X, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So X has to be in R5. Now find a basis. It means this is a math. If I want to solve, I mean the minimum number of vectors I need to cover all of the null. And it's simple. This is my basics. These are basically the, these are my basic variable. So I have 2 free variables, which intuitively tells me that the dimension is going to be 2 in this particular scenario. And now the rest is actually to solve. So I take a 0 and I solve. So this is 0, 0, 0, 0, 0. And I'm not going to rewrite. I'm going to put this one in here. And then it's just a matter of solving. So it's actually easy at this stage. 1, 2, 3, 4. No, we need 4. I solve. So I know that X3, X5 are free. And then I start rewriting the system. The bottom one tells me that X4 equal to X5. This tells me X2, 3X3 plus 7X5. And this tells me X1 is 2X2. Oops. Sorry, I wanted to do it better than that. Okay, I don't want to make it complicated at all. So I'm going to change this to 0, because I don't want it complicated. So it's going to give me 2x2. It's still complicated. All right. Why it is complicated? Not complicated. I will change. What do I have to do? So, what do you think I have to do to be able to get the solution easily in a neat way? This is not in reduced echelon form, right? It's not in reduced echelon form. My mistake, I was planning to give it to you in reduced echelon form. It's not in reduced echelon form. So to make it really easy to be able to pick up the solution, you have to go back and find the reduced echelon form, or you have to make back substitution to express everything in terms of the free value. So if we want to do it perfectly, I did not give you the reduced echelon form. I actually gave you the echelon form. That's my mistake. And then I will have basically to go and do more work with the problem. And which gonna give me 0, 0, 0, 0, 0, and a 0 in here. So those will be not problematic. And I'm gonna have 0, 1, -3, 0, -7, 0. So I'm gonna have issue with the first problem. Oh, sorry. And the first equation is gonna give me 1. I have to get -2. And it's gonna give me a 9, but then I'm gonna have -5 plus 5, was gonna give me a 0. Then I'm gonna have -5, was gonna give me a 10, -10, 10 plus 4, that's gonna give me 14 and 0. So I am now in a better shape but not completely better shape. I still have to make this into a 0, and then my problem will be way, way more satisfied. I will do my best to give you row reduced echelon form in the exam, because I'm not checking if you can add numbers. So 1, 2, 3, 4, 0, 1, 2, 0, 1, minus 2, 0, 1, minus 3, 0, minus 7, and finally, minus 2, that's a 0. I have to multiply this by 2, minus 6, that's a 3. My 0 is, I have to multiply this by 2, 0, and 0. And with this in mind, I am very safe. Now I can move on and solve the system without having to worry about anything. So now I'm solving the system. Of course, nothing changed in terms of pivot, but the solution is easy. So x3, x5 are 3. Now this is going to give me x4 is to x5. The first one is give me x2, 3x3 plus 7x5, and the first one gives me minus 3x3. And now I'm going to write in parametric form. I'm going to make this S and this T. And I'm going to have minus 3, 3, 0, 0, 0. And in T, I'm going to have 0, 7, 2, 0, 1. Sorry, I'm going to have a 1 down here. So every vector that solves the system is a combination of those two vectors. Those vectors will always be linearly independent. And, oh, thanks, Mika. Okay, those vectors will be absolutely independent. So the basis for the null is going to consist of those two vectors. If I have a stupid computational mistake, just accept it, because my plan was to give you in reduced echelon form, not only in echelon form. And the dimension here is again equal to 2. Now, if you have a problem and you have 3 free variables, then you're going to have, so if you're going to, so the dimension of the null is actually the number of free variables. If you have 3 free variables, so let us say I have like a 0 in here, and I have a 0 in here, so I have 2 basic 3 free variable, you're going to have 3 vectors in the basis. So the vectors you get here, we can prove that they always end up to be linearly independent. Okay. So that's it. That's the only new material that will be covered on the quiz. Is that easy or hard? Do you guys want this on your exam, yes or no?
Yeah.
Yeah?
Yeah.
Okay. All right. So that's the only thing I'm going to cover before the test. When we come back from after the test, we're going to start chapter 3, and we're going to learn determinant, and the last thing we study, which is the crucial idea, but it requires everything we did, was the notion of eigenvectors and eigenvalues. So now I stop myself for new material. So this null will be on the exam. Usually it's easy. The students don't have difficulties with it. And I'll go back to the exam and I'll answer any questions you guys have. Did any of you have the chance to look at the review and ask any question? All right, so what your test will be basically about, okay, I gave you the review. Is first I tell you, go over your quizzes and homework, definitely crucial. And the old exam, because it kind of guides you a little bit. So the test will cover linear transformation. So basically, what's a linear transformation? Transformation is nothing more than a function. It means it's a rule. You give it an input, spits out an output. In our class, the input is a vector and the output is a vector. That's really the main idea of transformation. Linear, it means it have an extra property. It's this preserved vector addition. It means image of the sum is sum of the image. And it preserves scalar multiplication. It means you take a vector and you stretch it and you find where it goes. It's the same thing as the stretching the image. Now the range, which is giving you a lot of trouble, the range for some reason. Number 9, Marcel, where? Marcel, number 9 in the review or in the book? I thought you were going over the, oh yeah, okay, sure. Very good. Okay, so linear transformation. So you will have a question along those lines. Algebra of matrices, crucial. I usually give the student like, multiplying matrices, just simple question, but just to make sure that you know the algebra of matrices, the property of the operation, absolutely, namely the product, and the transpose. It's important you know what the transpose is. The inverse, there will be always a matrix and you're gonna find the inverse. And usually the inverse, I always put a very X in it or an A in it, not only numbers. So be ready for that. So how to find the inverse? Using the algorithm, how to use it to solve AX equal to B, and all the properties of the inverse. So when I'm talking about property of the inverse, it means like inverse of A times B, let us say, is B inverse, A inverse, and so on and so forth. Now, invertible and non-invertible matrices. So here, I want you to go back to the invertible matrix theorem that we did before the spring break and all the mess we're in right now. So it means basically tells you if A is an invertible matrices, what can we say? So if a matrix is invertible, it means if you can find something that when you multiply it by to get the identity, what can we say about the matrix? A lot. The system X equal to 0. First of all, if A is invertible, its reduced echelon form is the identity. Once you keep this in mind, there are tons of things we can say. X equal to 0 have only the 0 solution. Actually, let me ask you a question, simple question. Suppose A invertible. What can we say about the null of A? Suppose A is invertible. And I'm going to find the null. What can we say about the null? I give you a minute to think about it and to connect dots. What's the definition of the null? And how can you relate it to the invertibility?
The only X that would satisfy that would be X equals 0.
Right. If A is invertible, the only vector in the null is going to be the 0 vector. Because the null is all vectors that solve AX equal to 0. If A is invertible, there is one of them, not two, one that satisfies this equation is the vector X equal to 0. So in this case, if A is invertible, then the null will consist of the 0 vector only, the 0 vector only. So it's a nice connection between the invertible matrix theorem and the null itself. So a matrix invertible, it means that the null is only the 0 vector. Okay. Now subspaces that we've been working with, basis of a subspace, and in particular, how to show that a set of vector form a basis for R2 or R3, because these are the easiest subspaces that we have. Dimension of a subspace, don't confuse the dimension with the basis. Dimension is a number, nothing more, nothing less. It's a number that represents how many vectors are in the subspace. And finally, the null space. So these are the idea of the exam. Now I gave you last year exam because I think it covers a lot of the ideas that we developed. So I will do number 9 from it. Let me look at it. Number 9, right there. It's a nice problem, number 9. Yeah, I will answer all those questions, but first let me about the test and how long. Now let us just go through, the mathematical question, all right? So here's my problem. I have T from R2 to R3. It's a linear transformation. So I'm giving you this info. And I'm telling you that this transformation takes the vector 10, 20 to 2, 7, and takes the vector 1, 1 to 5, 6. Okay? And then I'm asking you to find the image of the vector 34, 64. I mean, you see, you know, probably, okay, what's there? Is there any connection between them? But I gave you a hint, of course. What is my hint? I told you that. Start by writing 34, 64 as a linear combination of those. Why did I give you the hint? And why this will make the problem easy? First, let me write 34, 64. So first I'm going to write this as a linear combination of the 10, 20, and 1, 1. So you can do this basically in two ways. I try to give you easy vectors. Either you can kind of spot it, or you can solve the system. Can anybody, without solving, I will solve, write this as a combination of 10, 20, and 1, 1.
3 times 10, 20 plus 4 times 1, 1.
Yeah. Okay, so that's, I mean, because I gave you easy vectors, you can basically spot them. So, and if you cannot do them like this, you actually set the system 10, 20, 1, 1, 34, and 64. And you try to solve the system 10, 1, 34, minus, multiply this by 2, gonna give you a 0. Minus 2 plus 1 is gonna give you a minus 1. Minus 2 times 34, that's minus 68. Minus 68 plus that's gonna give you a minus 4. So basically I'm solving C1 plus C2 equal 34, 64. And these are my weight, 10, 20, and 1, 1. So I'm basically solving the system. So immediately we realize my C2 is going to be a 4, and my C1 is going to be, we have a 34 from here, and you're going to add the, no, something is wrong. Is anything wrong? So you get 34 plus 4, 38. What is wrong? Because we should get 3. Well, I'm not getting 3. Can anybody spot anything? 10, 20, 1,
X2
1.
is 4, not minus 4.
Yeah, I have that.
So you subtract 4 from 34.
Ah, thanks. Sorry. Which is equal to 3. Okay, so this is the linear combination. So that's the easy part. Now, what's the benefit of that? Why writing it as a linear combination is actually enough. So now we have, I'll go back to the problem. So my vector 34, 64 is 3 times 10, 20 plus 4 times 1, 1. All right, now can I find the image of this vector? Do I have the info to find the image? What do you think? This is 3 times that plus 4 times this. What does the linearity tell me? The image of this vector is 3 times the image of the vector 10, 20 plus 4 times the image of the vector 1, 1. That's where the linearity is playing a role. And now I am done because I know exactly what's the image of the vector 10, 20, which is 2, 7, plus 4 times the image of the vector 1, 1, which is 5, 6. And now I just have to add. That's going to give me 6 plus 20, 26. And that's going to give me 21. 21 plus 24 is going to give me 5, 45. And of the problem. Okay? And this is basically Linearity at work. So if I can write a vector as a combination of two other vectors, if I know where this one is sent to, if I know the image of this, image of that, linearity will help me to find the image of every linear combination of them. If I know the image of two vectors, I know the image of every linear combination. That's the linearity at work. Good. Any other questions from the exam? For those who looked at it, of course. Any other questions? All right. So I'll go through it a little bit and just to give you a picture of the type of questions you should be expecting, actually. So the first is a purely algebraic type. Here, my goal is for you to be able to basically use all the algebra of matrices. So I gave you two matrices, A, B, and C. And let X be a 2 by 2 matrix to satisfy this equation. And my question is find X. Of course, we've done problems like this before in class. So how to find the X? I just set it up. It will be up to you. So we're going to solve for X first. Usually students have no issue with this type of problems. We're going to subtract B from both sides. And now I need to isolate my X. So I have to left multiply by A inverse. Left multiply by A inverse, left. And this is parenthesis C minus B. The mistake usually that occurred in class, the student will multiply C by A inverse for getting B, which doesn't work. The rest is easy. A inverse, for a 2 by 2 matrix, only 2 by 2 matrix, it's easy to find the inverse. So just remind you, if A is a 2 by 2 matrix, you can either use the algorithm or you can use the formula, but it works only for 2 by 2. It doesn't work for anything else. So it's usually 1 over AD minus BC. And on the diagonal get switched, off the diagonal get multiplied by A negative. So with this in mind, finding A inverse is going to be very easy, and then you multiply it by C minus B. That's a typical algebra problem that I may give you. The second problem, again, I think I gave you that on your quizzes, if my memory is correct. I think, I don't remember. So you're given that AB1 equal B1A and AB2 equal B2A. What can you say about AB and C? And the whole idea is you set them equal. So you take A times B1, you set this equal to B1 times A, and you ask yourself, okay, if they are equal, what happened? You take AB2 and you set it equal to B2A, and then you ask yourself what happened in this scenario, and you find the connections between A, B, and C. I'm trying to see which problem. Number 3, again, that's a typical problem where I'm going to ask you to find the inverse. They will have X, Y, and Z. Some student, when I gave you a similar problem before on your quizzes, they gave the parameter X, Y, Z values, and they found the inverse for those values. This will not be accepted. If I give you X, Y, Z, you have to keep X, Y, Z and give me an inverse in terms of X, Y, Z. You don't give them specific value and find the inverse. And remember, finding the inverse, again, it's algorithmically easy. You start with a huge matrix. You keep performing grow operation till you hit A inverse. You have to hit the identity. You don't hit the identity, you cannot find the inverse. So that's the algorithm is easy. Now, this piece was mainly, again, algebra of matrices, true or false. The first one. I've gone through each one of them basically in class with you guys, but I want quick answer, true or false. Quick on the chat so I can cover a little bit more. False, absolutely, because AB squared is AB times AB, done. Nothing could be done about it. Absolutely false. B, true or false? Quick, again false, because if I multiply, I'm going to have A squared minus AB plus BA minus B squared. There is no way I can combine those. C, true or false, quickly. false, because I have a 2. And the inverse of that, the 2, we're going to become, it should be, so the correct answer is B inverse A inverse. Even if I had to give you numbers, if you have 2 times 3 for numbers, this is 1 over basically 2 times 3. It means a half times 3 inverse. That's really for numbers. It's also false for numbers. All right, D, true or false? I remember this one gave student hard time last semester. Okay, now D, I want answer for D. Okay, is false, everybody tells me false, true, okay, we're having trouble. Okay, let's see. Why false? Right, what is A square inverse? Let us understand it. Okay, it means A times A inverse. Am I correct so far? Now, what is the inverse of that? Usually we flip them, but they are the same one. So it's A inverse times A inverse, which is notation A inverse square. Absolutely correct. So that's a true statement. Now, if AB equal AC, then B equal to C, true or false? I want answer for E. Are the answers for E now? Okay, no, that's not a true statement. It's true only if A is invertible. If A is not invertible, and I did not tell you that, did I say A invertible? My apology. It's true because A invertible. Otherwise, it is not true. Okay, so it's true because A invertible. If I hadn't given you A invertible, this will not be a true statement. And then finally, this P, is it equal to C inverse? And I cannot answer this actually without actually taking it and kind of working with it. So if I work with it and I use every piece of algebra I've learned, so that's going to give me C inverse, B inverse, B, A inverse. That's going to give me A. Those two give me the identity, C inverse, A inverse. And the question is, can I go to C inverse from that? Yes or no? It's absolutely not, because I cannot switch it around. I'm stuck. That's my answer. All right. So this is for the algebra of matrices. A quick review. Now, this really, I still have a little bit. This is mainly the invertible matrix theorem. And the question is, let B be n by n matrix. And let us say that Bx equal to C, so I try to solve the system, is inconsistent for some C. It means you can find a vector C such that when I solve the system, so that's in my mind, so Bn by n, let me draw a picture, and then I can find a vector C such that when I solve the system with augmented matrix BC, this is gonna give me inconsistent. That's the picture. So B is n by n, somewhere that there is a vector that caused the inconsistency. And the question is, determine which of the following statement must be true. All right. The equation Bx equal to 0 has more than one solution. Must this be a true statement? All right. Now the chat should start for this question. Absolutely, it has to be yes. Everybody is correct. Why? If this is inconsistent, it means when I'm going to reduce, what's going to happen? If I'm going to reduce, it means this one, this particular C that causes inconsistency. It means if I'm going to reduce one of the rows, we should have something like that, because it's inconsistent. So what this is going to give me, remember that's in n by n matrix. The n by n matrix, if this is all zeros, it means one of the columns has no pivot. because it's n by n. So let us draw the picture to make it a little bit simplistic for us. Instead of taking n by n, let us assume B is 3 by 3, because this is really easier for us to interact with. So if BC is inconsistent, it means that's the picture. There is a pivot right here, 0, 0, 0. That's what has to be. And then I don't know what happened here. It doesn't really matter, but I know one thing. Sorry, that there is, this row is all of 0. So since it's a 3 by 3 matrix or n by n matrix, and the last row has no pivot, it means one of the columns has no pivot. If one of the columns has no pivot, it means I have a free variable. Let us assume this is a free variable. Being a free variable, it means when I switch to the system B0, because that's the homogeneous system they're asking me about, I'm gonna have a free variable right there. Free variable implies immediately infinitely many solutions. So the inconsistency will cause the last row not to have any pivot. If the last row has no pivot, it means immediately that one of the columns has no pivot, because the number of columns equal to the number of rows. This causes free variable and infinitely many solutions. Now, part 2 is the columns of B span Rn. It means every vector in Rn is a linear combination of the columns of B, true or false. The chat now is for B, absolutely false. The vector C itself is not in the span, because the system Bx equal to C is inconsistent. Means if I try to write C as a linear combination of the column, I'm gonna get absolutely inconsistent system. So definitely false. This vector C itself is not in the span. Very good. The matrix B has a pivot in n pivot. Absolutely not. Again, it's a false. And finally, the columns of B are linearly independent. Again, it's false, because Bx equal to 0 has more than one solution. The columns fail to be linearly independent. Now, in each part, the question is, back to basis, find the values of A, if any, for which the vectors will form a basis for R3. So instead of asking you, are those a basis, I'm asking you, okay, which A will make those vectors a basis? Okay, part A. Is there any value of A which can make those vectors a basis? Yes, no, justification. Okay, I need 2 more minutes and then you guys will be on your own. Okay. Is there any vector of A that will make those 4 vectors a basis for R3? What do you think? No, because they are a linear combination of each other. The answer is absolutely correct. Those are 4 vectors in R3. And any 4 vectors in R3 are linearly dependent. So no matter what A is, those vectors are linearly dependent, so they can never form a basis. Regardless what A is. Regardless what A is, they will not form a basis because they are linearly dependent. Now B. What's your answer to B? Is there a value of A that will make this a basis? Again, quickly, I would like an answer. Okay, so there are 2 vectors. Can they ever form a basis for R3? So R3 is my subspace. Means I want vectors that basically cover all of R3. Again, no value of A will do that for me because 2 vectors, when I span them, I take the span of 2 vectors, I cannot reach every vector in R3. So those, again, regardless what A is, they do not form a basis. Now C is problem. Which A will form a basis? If I have 3 vectors, I know that they can cover all of R3 if they are linearly independent. So this is really the problem boils down to find the A such that the vectors are linearly independent. So how do we find this? Again, we solve the homogeneous system, 0, 0, 0. And we solve the homogeneous system. This is 1, minus 1, 1, 1, 1, 0, 1, 3a. And we solve it. And then we ask ourselves, which A will give me a linear independence? Now, if we solve it, and you guys have the solution, we're going to have 1, 1, 1, 0, 1, 2, 4, sorry, 0, and 0, 0, A plus 1, and 0. So the question is, which A will make them linearly independent? For those to be linearly independent, I need a pivot in every column. I have a pivot column 1, pivot column 2, so I have an issue right there. So they are, yeah, it's blurry. Okay, I will zoom and see if this, okay, we're done. So A plus 1, which value of A will make them linearly independent? Anybody? Yeah, A plus 1 to be independent has to be different from 0. That's what causes independence, because I need a pivot in here. It means A has to be different from minus 1. So the three vectors will form a basis as long as your A is different from minus 1. If A is minus 1, they will be dependent, and then the ends of that. Okay. So please finish the review. It actually covered most of the stuff we've done. And back to the your exam. Your exam, you will have, okay, the class start at 9:30. I will upload the exam by 9:20. The exam will be on Blackboard at 9:20. Okay, so which give you between 9:20 and 9:30. For those who like to print their exam, you will have plenty of time to print it in 20 minutes. For those who don't want to print it, it's okay with me if you don't print your exam, but I want it to be written in a very clear way. Remember, I have 50 students in your class, and if you guys don't give me something very clear, I can't read it and I cannot grade it. So please be clear, like get ready with nice sheet of papers that you're gonna do your exam on. So I will put on Blackboard at 9:20. It will be uploaded into Blackboard. You guys can start at 9:30, and okay, 9:20. So I will close it at 11, like 11:10. It will be closed. It means you have to have uploaded by 11:10, unless. Okay. So during the exam, it means between 9:30 and basically 10:50, during this time, I will be on Zoom. So I want all of you basically to log into Zoom, to join the meeting between 9:30 and 10:50. I will be there to answer any questions you have, because you may have questions during the exam. So I will be physically there. So I want you guys to be on Zoom during the exam. Okay, please be on Zoom during the exam. And if you have questions, you can use the chat and ask me privately, of course, not for everyone. So the question will be private for every one of you. If by coincidence I did any mistake in the exam myself, which always can happen, and then I will put it on the chat for everybody to see. Otherwise, if you guys have any question, you can chat with me privately. I will be there during the time of your exam. So I repeat, the exam will be on Blackboard at 9:20. You can start at 9:20. If you can print it, it will be very good, because that makes grading easier. And if you can't, I want the problems to be in order. So I don't want you to do problem 1 and then problem number 5. I cannot function this way. You have to put them in order. That's why I will appreciate if you can print it. That's why I gave you 10 minutes to do that. And the exam will close at 11:10, which is going to give you plenty of time, I hope, to do everything. Please upload it on Blackboard, not email. All right, any other question before I let you go? Okay, remember I have office hours at 12 o'clock today, from 12 to 1:30. And I have office hours tomorrow from 12 to 1:30. If you have any question, please join me. Okay? Okay, good luck and stay safe. Bye, guys.
One last question.
Yes, please go ahead.
Obviously, you'll have the answer key for the past exam and the review uploaded.
It's on Blackboard.
Yeah, but what about the lecture for today?
The lecture is on Blackboard.
No, like today's video, like the Zoom.
It will be
lecture.
on Blackboard. What
Oh,
else?
All right, okay.
All
Sorry.
the videos are on Blackboard.
All right, I just thought there might be a delay just because like we.
There will be a delay because I have a class right now.
All right, okay.
So I won't be able to upload it till later on because I have a class at 11, so I cannot do that.
All right.
But
okay.
everything we've done so far, every video is already on Blackboard.
All right.
All right?
Thank you
Anything
very much.
else?
Not
Okay. Bye-bye, guys. Good luck.